Sorry, yeah, Kasim, would you like to mute your mic? Great.
Oh, sorry. Okay, yeah.
Yeah, because there's, I think it's called positive feedback that we're getting. All right. Python in basic engineering data analysis. Again, please, at the end of the presentation or workshop, if you can submit your feedback to this URL, which I'll put into the chat box. There we go. Much appreciated. And at the end, I'll remind you again. So essentially what we'll be looking at in the next hour or so is some things in engineering that can be done in Python, like symbolic math, fast Fourier transform, numerical integration, control systems, some modeling and visualization on the engineering side, and data analysis side again. Looking at arrays, data frames, a bit of data cleaning, getting some basic stats from your data, data mining, which includes things like classification, clustering, etc., and what I call data processing, modeling, and data visualization. So to start with, these libraries under engineering are essential libraries that you should install in your, if you like, environment. But now NumPy Pandas you should have already installed, as well as the matplotlib, but you may need to, or you should really install SciPy, Open PyXL, Control, and SymPy. And on this side, again, matplotlib appears again. Pillow. Oh, sorry, that's wrong there. That's a typo. And which it should be really, this is really the, what should be there, and the SCI kit -learn libraries or packages that you can install using pip or conda installation program. Now, some important conventions when you're importing packages and libraries and methods, modules from these packages. It's far better to use this type of notation rather than this type of notation, because this will essentially import everything, and you don't really need everything from NumPy. You can be more selective. Now, to find out what you can actually import and what's useful to you, there is obviously documentation available for each of these packages, and it's well worth looking at the documentation. Now, one word that, or words in fact, that are familiar or used commonly in data analysis type of jargon, if you like, are munging, munge, and wrangling, which, as I said, my background isn't actually data analysis, it's control systems. So these are, as I said, some terms you may hear in the area of data analysis, which, and all it really means is to put in your data in a structured form and clean it up, basically. So Python and engineering. Now, one of the things that is nice is the symbolic variables, and you can do algebra with symbolic variables. So essentially, these two line or packages you need to install, and again, you need to install SymPy. So it will be basically the old pip install in the terminal window to install SymPy, a NumPy you've already installed. So what we're doing here now is declaring our symbolic variables x, y, z, and dx. Now, once you've done that, you can do things like this. You have an expression here, and you can actually, using the expand function, expand it and print it out. So if you have this type of situation, just put that aside while I get the file ready. And admit some more people. Right, so we need to look at this. Well, I need to look at this, in fact, just bear with me while I get the, okay, so that's the file name. So here, it's two symbol algebra. That's the file that I'm opening up. So again, documentation about SymPy you can find at this particular URL. And prior to using any of the SymPy functions, you need to do a pip install in your terminal window here. So again, we're importing the modules that we want, creating our symbolic variables, and here now I'm going to expand this particular expression. In this case, what I'm doing using the simplify function, as you can see, simplification is not a well-defined term, but there are strategies for simplifying things. And again, you should read the documentation on the use of the simplify function. Here, in this particular case, again, I'm using my SymPy from this module here and finding the limit of cosine of x from x to 0. All right. And in this particular case, I'm finding the same function, the limit of x to infinity. And there are two ways of, there are more than two ways of symbolizing infinity, but one way when you're using SymPy is to use this particular notation, which is 2 zeros, well, not 2 zeros, sorry, 2 lowercase o's, and this will print out the limit, if you like, of cosine of x from x to infinity. Again, when you're dealing with equations, linear equations, and algebra, you can actually solve two linear equations like this, for example, and the parameters that you are interested in, which are variable x and variable y, using the solve. So you algebraically solve equations and systems of equations that you can build up in Python. But if I actually run without debugging, we'll see it takes a bit of time. So this is the expansion of this term here using simplify, which is trying to simplify this. I get a result of that. The limit of cosine of x from x to 0 is infinity, and from x to infinity is 0. And again, the solution of x and y for these two linear equations that I'm highlighting is -3 and 1. -3 being x and 1 being the value of y. So that is something that's easily done in Python. Similarly, a very useful thing in engineering is differentiation. And again, we're importing our packages, creating our symbolic variables. And here I'm using the diff, if you like, method of finding the differential, the first derivative, if you like, of cosine of x. And this is a variable that I've assigned the result to be shown in or stored in. And this is just printing it out. Here now, again, I've already have my equation, but notice this time I'm actually stipulating x 2 times. And what this does is it finds the second derivative of the cosine of x that you have. Here now, I have another expression, the exponential of x cubed, and I'm finding the first derivative again using the diff method. And again, so on. This is the sine of x, y, z, and I am finding the first differential with respect to x, again using the diff. Here now, I'm finding the first derivative of x with respect to x and y, and here I'm essentially first derivative with respect to x, y, and z. Again, using this diff function. Now, here I'm demonstrating the use of another function called derivative, and essentially there is a difference. The difference between the diff and derivative, if you like, functions is that a derivative will just take the derivative of a function, whereas this diff, will take the derivative of a function, whereas this function here, derivative, creates an unevaluated derivative of a SymPy expression. So this, as I said, finds the, if you like, the derivative of a symbolic expression and an unevaluated derivative. And you need to actually display it. You need to use this essentially to actually create or print the derivative out. So let's just see the code for that. Now this is this is the file that I'll be using, which essentially controls the various derivatives. Now here, my terminal, I'm just going to clear it now and go run. And as you can see here, the second derivative, first derivative is shown in this window here. So I've got the first derivative of cosine x is minus sine x. The second derivative of cosine x is minus cosine x. The first derivative of this expression, e to the power of x to the power of 3, is this expression here. Now, print dollars, $50 signs, is essentially this statement here. And then I am printing the first derivative of this function with respect to x, which is this. Then I'm printing out this expression, which is again this first derivative, but with respect to x and y. And finally, again, sine of x, y, and z with respect to x, y, and z, which gives us this expression here. So that is something that, as I said, can be done fairly readily using symbolic, if you like, notation. and symbolic algebra and using the correct package. You can also do partial derivatives, and partial derivatives, again, importing packages, creating my symbolic variables, and I'm going to do if you like, partial differentiation of this expression here. So here, in this statement, I'm creating the function, again, using sympy, which is this, if you like, object here, and using the diff function, and then printing out the result of this differentiation. Similarly, I can use the derivative function and partial derivative using this. And again, you've seen the slight difference in the coding structure between using diff and derivative, but you have to implement this. So now if I have an expression like this that I want to differentiate, again, I build up my function. So this is my function. I feed my function into the derivative because it's essentially an expression. And notice here the 2, I'm doing dx, dy2, dz to the fourth. The y2 is implemented using this, and the x to the fourth is actually implemented using this expression in the derivative function. And x, obviously, there's no need for 1; it defaults to 1. So, and again, the seventh you've got. The reason that 7 is there is fairly obvious. 4 and 2 is 6 and 1 is 7. So it's d to the 7th of dx, dy squared dx to the 4th of this particular function. And hopefully it will print out the correct answer. So good question. And what if you look at? Let me just get the code for this particular expression. Notice here I have that's the example. So let's go run, and this will answer your question. So it's actually produced this thing. Now, if I change this to the lowercase run, and it says attribute error, no attribute derivative, because if you remember, as I said in the first session, Python is case sensitive. So if you don't use the case sensitivity in your program, you're going to get errors like this creeping up. So I said it's well worth reading the literature about the particular function name and how you do it. And even if you're assigning a Boolean variable to true or false, if you use lowercase letters for F and T in the words true and false, Python will flag up an error because of its case sensitivity. Okay. Now, why are some functions named with capital, others with small? I am not sure what the reason is. To be honest with you, all I know is that some are defined with a lowercase letter and others with an uppercase letter, and you have to use the correct case for the function to work properly. Okay. So that said is something that I'll actually investigate as to why there is the difference, and hopefully get back to you at another date. So partial differentiation. And obviously with differentiation in engineering, there is integration. And again, now I've cut out the bit of code importing my packages. So essentially what I'm using is the integrate function of SymPy, and I'm integrating cosine of x. Here now, I'm integrating sine of x, but I'm actually giving, if you like, a range from 0 to 3 pi. And again, notice here, I'm using MP, which is an abbreviation for numpy, so it's 3 pi. And again, somewhere here, I would have, above in this area, I would have done the import numpy as MP and import SymPy as SYM. And similarly, what I can do is again use e to the minus x, and here I'm using a slightly different notation for x from 0 to infinity. Now, infinity INF is a standard sort of form of representation. You can use that. I think in MATLAB, if you do a division by 0, it brings out the inf message. And again, I'm changing the string inf to a float, and Python recognizes that I am actually talking about positive infinity. So here I'm evaluating this expression from 0 to positive infinity for e to the minus x. Similarly here, I have this expression, minus x squared minus y squared, x, if you like, from negative infinity. This is in fact a double integral, okay, to positive infinity, and then y, the limits, if you like, I'm declaring the limits, again, from negative infinity to positive infinity for y. And again, the brackets must match correctly, otherwise you're going to end up with errors when you try to run your code. So if we have a look at this, let me have a look at which file, symbolic int. Okay, so if I get the right file, symbolic int, this one here, this is symbolic integration. Let's try again. That I just showed you. So if I run this particular code, which is this is the name of the file, what we have is some results. So it says the integral of cosine of x is sine x. The integral of sine of x from 0 to 3 is 2. The integral of x squared plus y squared with respect to x, y, the limits from 0 to infinity is 1. The integral of a, which is this one here. So this expression here is pi, and the last expression here, bb, is, or the limit, in fact, from x0 is 0. Which I think I've checked a couple of these using other packages to double check that the results are correct, and the ones that I've checked, expressions that I've checked, were in fact correct using other software packages. So you can do integration, and again, which is this one here from x to 0, which is fundamental in engineering. Now, a useful, if you like, technique is the Fourier Transform. Now, I'm not going to talk about the maths behind the Fourier Transform, but in very simple expression, what you have, you've got something in the time domain, and then you transform it, and you get if you like, a result in the frequency domain in very simple terms. So again, here now, I've included something called Signal and Blackman. I don't know if there are any engineers, electrical engineers amongst us, but there's something called windowing and Blackman windowing. So you can actually do some windowing of your system. For this particular example, we're not going to use this Blackman's windowing, but what we will be using is FFT, FFT free, possibly FFT shift. So here now, what I've got sampled data points. This is the sampling space between my data points. I'm creating an array of X points here using linspace, which is similar to linspace in MATLAB package. So we have the start value, the end value, and the number of points. And then here, whether I think include the end point or not. Now, having generated my sample points, I'm creating Y1, which is a sine wave of a frequency of 5 Hertz and an amplitude of 0.8, whatever units I happen to be using. And similarly, I've got another sine wave, Y1, which has a smaller amplitude and a higher frequency of 10. And then I'm actually summing the two sine waves and plotting them out. So this is showing you this here, all these functions, if you like, that I'm doing come from my matplotlib library. And essentially what it's doing is showing you the sum of the two individual sine waves as well as the individual sine waves on a plot. Here now, I'm using the FFT function, which is part of SciPy, another library that you need to install in the Python environment. And again, here I've got sort of the number of sample points, the sampling space, and this is essentially a integer division of from 0 to n. So I created an array of points from 0 to n with no remainders, if you like. And then I'm actually plotting this frequency component in this function here. And then this, if you like, is the set of X points, and this is the set of Y points in the plot. And what this results in, again, and then adding a grid, some layer annotation to my plots. So what this results in is essentially the first plot, which shows me my 0.8 amplitude wave, which is here, 0.8, as you can see. And then this, the orange wave is the 0.4 wave, and the green, if you like, this wave here is the summation of Y1 and Y0, which is my signal, if you like. And what it's done is Again, so this is in the time domain, and now I've got, after the transformation, I've got that information in the frequency domain, and what it shows me is that the main components and their amplitude. So that I've got the frequency component here, which, if you like, corresponds to 0.5, and then 10 is this component here, and again I have an amplitude of 0.8, which is shown here, and an amplitude of 0.4, which is shown here. So again, if you have a wave and you want to find out the main components that constitute that wave, the FFT is one way of doing it. And you can essentially reconstruct the base components of your total waveform. And it's used in various, set of analyzing various waveforms in control system engineering, in communications engineering, and I imagine in other types of engineering as well. And now a quick look at control systems. Now what I'm doing here is actually using or modeling a spring mass damper system, a very basic spring mass damper system. So again, in control engineering, you would need to import the control package, and then you can use various features of the control system package. And again, there's a lot of similarity in Python with MATLAB, and again, it makes it easier to go from Python to MATLAB and vice versa. So here I'm creating some data for my mass, my spring stiffness, and my viscosity in my damper. I'm creating a state space model of my system, essentially from the differential equations that correspond, if you like, to a spring mass damper system, which is essentially a second order differential equation. And here now I'm using the SS function to create, if you like, a system from my A, B, and C matrices. And I've got normally you have a D matrix. In this case, it's actually 0. Then I want to plot, do a transient response of my basic system to a step input. I can actually use just step, and this is my system. And then I want to plot out the, if you like, the time and the amplitude of, or the output of my system. So the input is a step to my system, and I want to find out how the system behaves to that and plot out the amplitude. I'm creating a grid here and then plotting the T and the output of that response from the two, if you like, the two arrays of data that I've created in Y out and T. I want to get the individual points out here. Similarly, I want to look at it in the frequency domain using Bode or Bode plot. I can also create a Nichols chart of my system. I can also do a root locus and see how my system behaves in real time, if you like. So let me just get the file to show you the code. So that should be CTRL, control system 1. So this is the essentially what I just went through. And what this code will actually do when I run it, it takes a bit of time because there's quite a lot of processing. So it produces the step response of my second order system. So it from there, from this overshoot, this is the steady state value, 0.025, but it's got an overshoot, and this is time on the axis. So I've got this figure here. This is the Bode plot for my system. This is the Nyquist plot for that particular system. It doesn't encircle the -1 point, so it's a stable system. If I remember right in my control system theory correctly. This is a Nichols plot. Again, if you're looking at phase characteristics in such systems, it's Nichols plots are very, very useful. And in practical applications, if you're looking at PIO, pilot-induced oscillations in aircraft, Nichols plots come in very, very useful in looking at pilot behavior. And here we've got sort of root locus in a window, and obviously if I expand my window, you'd see the root locus essentially going parallel to the imaginary axis here, which means that as my roots go up, follow the trajectories, if you like, of the root locus, the damping becomes less and less, but it doesn't become unstable. My system doesn't become unstable, which is important for a system. So that is essentially building a state space representation of a spring mass damper system from the differential equations, or equation, in fact, the first order equations that result from such a system. And again, this is just a summary of the type of plots that can be generated in Python. Now, you can also do a bit of control system manipulation. Now, this here is a sort of general block diagram where you have a system, G of S, that you're trying to control, and you have some feedback from your sensors, and obviously they've got sensor dynamics, etc. So this is a basic system, and usually you look at the single input, single output, and you're looking at the outputs in the Laplace domain. Typically, such a system has this type of transfer function here, and this is the closed loop transfer function, G of S divided by 1 plus G of S multiplied by H of S. And if you look at it very simplistically, you can see that there's going to be some damping involved, because you've got this term added to 1. So whatever ratio this is, it's going to be a bit smaller, given that you've got negative feedback. If you have positive feedback, then obviously could be catastrophic, depending on your application. So also in control systems, you have what are called PID controllers, which are proportional, integral, and derivative controllers. And they are of the form, they have if you like, a proportional gain, an integral part denoted by Ki over S, and what I call a pseudo differential part. Rather than having just the S term, practical implementations, you have an S over S and a time constant plus 1, and usually you try and make this T of F a small value, so you can approximate that this is almost 0, if you like, So it gives you KD S over 1, which is your differential term. But in reality, this is what is actually implemented. And there are very good reasons for doing that. So with this type of idea behind us, supposing you have a plant, which is your basic system, you have your controller, and we have perfect sensors with perfect sensors dynamics. So our H of S can actually be represented by unity gain. We don't lose anything from the feedback of the output. So typically, if we take our transfer functions for our PID controller and our G of S, which is our plant, typically something like that, in closed loop form, it gives us this sort of transfer function that we have here. And this is essentially G of S 1 plus G of S H of S, where our G, this, if you like, is our new G of G of S, like that. Okay, very simply. And to implement it, we again do our imports from various libraries. Now here, again, because we're using some of these nice features from the libraries, what I'm doing here by using transfer function, and again, you've got to make sure the case correctness of the name is correct. I'm creating a Laplace variable S, if you like, or Laplace S. And then I can use this S in a transfer function to create a transfer function. So what I'm doing, my G1 of S is this particular transfer function, and I'm taking this function, creating some output after I inject a step into the system. So what I'm doing here is actually looking at my basic system, injecting a step and seeing the response, the time response to that system. And this is what really this does. Now here, based on the results of this bit of code here, I may not be happy with my system, so I want to include a PID controller. So here I'm setting up the constants of my PID controller. Now I'm manipulating my PID controller. If you remember, I had a K plus Ki over S plus KD with a filter. Now, if I want to put that PID controller into a transfer function form, I can do it this way. So I've actually created a transfer function of my controller. So I've got G2. G2 is my PID controller, and G1 is my plant. And essentially what I want to create is G1, G2, and then my sort of feedback control loop like this. And we said I have unity feedback, it's a minus sign, and then I've got my input and my output signal here, like that. So I've created my G of S and G of 1 in terms of transfer functions. You can do it in state space, you can do it in various ways. And here now, I'm creating my overall transfer function. So what I've done is, I have said, okay, I'm going to have input. This is going to be my G3, and I'm going to have G3, sorry, G3 here, and I'm going to have an output like that, out. And look at the step response. So without further ado, as they say, let's have a look at what happens to this system. So this is the file, control sys 002. So when I run it, oh, sorry, That's actually the wrong, that's something else. That's the wrong model. My goodness, getting carried away here. There you go. Is this the one? Where is it? Yeah. I've lost my model. Just a moment, please, while I look in my files control. Oh, this is the one, PID. There we go. That's the example I was looking for, PID. So now when I run it, let me just make sure I stop debugging from my previous run. So now I will run this particular model for my PID controller. And what happens is I've overlaid the two responses. So this blue response is my basic time response for the plant by itself. And as you can see, I've got here, I've got something like a 40 odd% overshoot. And this orange response is my PID controller with unity feedback. And the response is about, the overshoot, I should say, is about 10%. Now, how do I know that? If you look in this corner here of the plot, when I move my cursor over, I actually get my X value, which is my time value, and the Y value. So it's essentially 1.117, which corresponds to about 11%, 12% overshoot. And here, again, I've got a time value of 0.6 and an amplitude value of 1.406, which is my 40 or 41% overshoot. And now essentially you can simulate this model in MATLAB, and you'll actually get similar responses and values for this particular system that we were looking at, which was which was here. This transfer function here to sort of match your Python model with a MATLAB model, for example. Now, one other thing that we do is in engineering is numerical integration. Now, numerical integration is different than analytical integration, if you like. And numerical integration is gives you an approximation. It's an algorithm, essentially, to the integral. And there are various integration methods available in Python. And again, depending on the type of equation or system that you're trying to integrate, you should really look at the literature, because they are different, and you get erroneous results if you use the wrong numerical integration method for your particular equation. Now, to get the ball rolling, I'm using the simplest of methods, which is really the trapezoidal rule of integration, and this is using NumPy in this particular case, NumPy trapezoidal Z. And what this does is I'm creating my integration, if you like, step length. I am creating a set of points from my lower limit to my upper limit. And I'm actually doing a, again, which is, that is actually a mistake here in the PowerPoint. And it will produce, let's have a look. This is the code. That's the correct code. So yeah, we've got lim space. This is my function y equals x squared, and I'm feeding the array of y points, the array of x points, and my integration step length. And here I'm actually using another method called the quad method, and the quad path, which dates back to the Fortran, days of Fortran of long ago. So now, if I run these two files, or sorry, this file, what you'll see is the trapezoidal method produces a value of 0.3335, whereas using the two typos here. Using this particular quad function, it produces a much more accurate result, as you can see from here. And this is actually the error between the, if you like, the real and the analytical numerical solution and the analytical solution, which is pretty small indeed. So again, choosing the correct integration method is important, and it really depends on the type of equation that you are trying to integrate. Similarly, you can integrate equations like this, or double integral. Again, here now, instead of using NumPy trap Z, I'm using the SciPy integrate method. Here, I'm actually defining my function that I want to integrate, which is xy squared, which is this function here, and putting it into a function. This, again, I've defined a function. These are what I call one-line functions, and all I'm doing is actually creating the lower limit, which is this 0, and the upper limit, which is this limit here, but as a function. And here now I'm using the double quadrature function or method. And as you can see, f is the actual function that I'm feeding, which is xy squared here. The 0 and the 1 are my, this is essentially the lower x limit and the upper x limit. And g and h are essentially my lower limit and the upper limits of the, if you like, this integral term here. And this will actually produce the integral of this particular function that I'm displaying. So if I just let me catch up for a minute, numint 002. So I'm just trying to find, yeah, there it is. So here I've got my data creation and using the SciPy, which is what I showed you before. And the next one, which is the double integral, I think is this one. Yeah, this is the one. And you can also do a triple integral as well, depending on your function, using another method. Here, essentially, I'm defining my function that I want to integrate, the lower and upper limits, and I'm using the, this particular case. If I run this file, now I've got an error in my triple integral somewhere, because it's evaluated this double integral. So that's why the best thing to do is to actually get rid of this code here in this file. So let me just go File, Save As. And then just delete that code here. So I've got this simple code to do the two integration methods. Just clear my window and run. And it essentially gives you the value of the double integral and the sort of error value. And that is, again, using integration functions in Python and in NumPy and in SciPy. Again, read the documentation and select the right method. You can also, again, ordinary differential equations are very important in all forms of engineering. Here, what we have is, again, importing the various libraries. Here, I'm actually using a what's called a Lambda function, or Lambda. So this is the input to my function, and this is the actual function, x squared. It's a one-line function for very simple functions. You can use this Lambda notation, which you'll find in the first presentation of session 1. And again, here I'm actually creating my data array for x. And now I'm using this solve _1 VP, which is part of my integrate. So this is a specific tool to evaluate the function. Now, in this particular case, you'll notice that here, the difference between this line and this line is this. So in the first line, for A, I'm actually using the Euler method to solve the integral, and in the second method for B, I'm actually using a fourth order Runge-Kutta method to do the integration. And this will give you different, well, you'll actually see what it will give you. ODE. So when I get the file, ODE file. So this is the the file using the two different methods. Again, if I just clear my window, terminal window, run my file, what we have is sort of events none and the values of using the two different methods, and the sort of solution, and what other events you have, and you compare the two sets of values, if you like, for your integration method. And similarly, depending on the type of equations that you're trying to solve, you need to choose the appropriate integration method. So if you look into numerical analysis literature, whether you're using MATLAB or Python, you've got to make sure that you're choosing the correct or the appropriate numerical integration method to solve the type of equation that you are trying to solve. So that comes to the end of the engineering part of the presentation. Well, we come to a bit of Python and data. So here I'm using another package which I've installed, the OpenPyXL package, and again I'm importing particular features or modules, if you like, from that package. So here I've created a workbook object, and I'm activating that workbook object. In that workbook object, I have a particular cell address, and I'm assigning the value 888. Now I'm taking that particular workbook object and appending, which is one of the, again, methods that is available in OpenPyXL, 4, 5, and 6 and then appending another row of data 7, 8, 9, and 10. I'm also importing the date and time, which is like a data and timestamp, and assigning it to the cell G2. And using the save, I'm essentially saving these Python variables in this particular Excel file that you see here, which is in my default directory. So if I go to my default directory, let me just see now, default directory. And it's PYXLS. PYXLS, let me find it. Where is it? Ah, there we go. So if I open the Excel file py2xl, which is Python to Excel, what you see now is in this Excel file I've got 888 in A1. Underneath the row I've appended 4, 5, and 6 in different cells, and then subsequently 7, 8, 9, and in cell G2, which was this statement here, I've did a date stamped and saved my data in an Excel file. Similarly, I can open an Excel file. Again, I create a workbook object, if you like, using this particular method. This is the file that I keep my data in, and essentially I've got some, sorry about that, cell objects 4 and 5 that I can get from my Excel file and assign them to a particular variable in Python. So if I just get Excel, my Excel to Py. So this is the Excel file. So essentially all I have is a bit easier to see, table full of data like that. And then I want to essentially implement it in my Excel file. So to do that, let me just get the appropriate Excel. So I have this Python file, as you can see. So this was doing the Excel part of the writing to the file, and this essentially is opening up my Excel file and assigning it to a variable in Python. If I run this program here, what I should get after it executes, run, is a set of values 14, 14, and 18. So what I've done here is I've taken a particular cell value, so it's in the 5th row, 4th column, which is the value 14, and assigned it to cell object, and then I've taken the value of that particular cell object, if you like, and assigned it to x and multiplied by 2, and hence it gives me the value of 28. But this is, again, a way of extracting data from your Excel file and manipulating it in Python. Now we've got arrays, subarrays, and arranging items. So we've got, again, I've created an array using NumPy, and this is the way that we define arrays. And notice this and this square brackets, as well as the pairs of inner brackets, to define, if you like, a 1, 2, 3, 4, 5, a 3 by 5 array of values. So we've got arrays and values here. So it's arrays 1. So let me just get the correct file to open. Arrays 1. So this is my, so if I click on run again, what we have is x1, x2 being generated and essentially reshaping. So this is x, x1 and x2, x, x1 and x2 arrays, as you can see. Here I've used the range. Now notice that because I'm using NumPy, I have to use a range as opposed to range from 1 to essentially 12. So this is the range of values in my array 1, and then you can reshape using the reshape function 3 and 4, and what it's done is it's created this array of values, a 3 by 4 array from this particular array of values. And there are a whole host of things that you can do with arrays in Python in terms of shaping them. You can concatenate arrays together. So here I've got 3 arrays, x, y, and z. Oh, sorry, x, x1, and x2, and I'm basically sticking them all together. You can vertically stack arrays. You can horizontally stack them. You can split arrays. Right. NP arrange is Khalid, because I'm using NumPy and arrays in NumPy, I have to use a arrange. If I was just using Python without using the NumPy package, I could use range. So that's the difference. Range is for Python, and a range is when you're using NumPy, because essentially arrays and matrices in Python are a bit awkward. It's much easier to manipulate arrays and matrices using NumPy than just Python. Because in Python you've got to treat them as lists and manipulate them as lists. But that's the difference. So again, you can split them in different combinations. Once you've attended them, you can also do simple math. Like if you have an array, you can subtract 3 from each of the elements, or you can square all the elements in your array. You can find min and max values in a particular array using, again, NumPy and the min max value, which I'm not going to demonstrate. It's fairly easy to do. Again, quite a lot of things that you can do with arrays using the NumPy array and its suite of functions. But Pandas is essentially it's a 2-dimensional size changing and potentially heterogeneous tabular data structure with labeled axes, which is basically rows and columns. You can label rows and columns, which makes it nice. Now, this particular file I used to demonstrate some of the power, if you like, of the data frame. And if you bear with me while I get the correct file, DF taxi. Okay, DF taxi. This is the one. So this is the actual code that I'm going to run. Okay, so what I'm doing is importing the right libraries and the bits and bats for the libraries. I'm doing a timestamp here. So this is this point in time, and then I'm doing a timestamp after it's actually processed and done all this, if you like, code execution up to here. So that's when the timestamp is. And what this actually does, and it uses what's called a data frame from the Pandas library. If I go run here, it will take a bit of time. So here you can see it's the first timestamp in milliseconds, and it will take about 2 minutes, possibly 3 minutes to process. And you may ask yourself, why? Well, the first reason is my laptop is it's a 10-year-old laptop, so it's not particularly powerful. I think it runs an i3, or is it an i5 processor? So that's one reason why it's particularly slow. But it's actually finished now, and this is the sort of the second timestamp here. But what it's done is it's imported a CSV file, okay, an Excel CSV file, which has 7.6 million rows and 18 columns in it, okay? So it has, in fact, 138 million separate data items, okay? It's also, the program checked each of the columns to see that there are no silly values, and I think it's NaN values, again, or null values. I'm checking for null values, but you could check for other types of data, missing data, for example, null data, string data where instead of numeric data, etc., etc. And in this particular column, it's found that I've got some null data, so it's informed me some null data. And then it's done some basic stats. It's looking at the column fair amount and found the mean, the min, the max, the standard deviation, and the variance of, if you like, a column of 7.6 million items in less than 4 minutes. So this is really the power of using data frames. And you can, as I said, you can have mixed data. You can have, as I said, heterogeneous or non-heterogeneous type data in your Pandas table and manipulate that data using some of the functions that are available to your data frame. So again, here, this is another example as well, which is, I think, is really nice. Data read. Now this, again, using the idea of Pandas and the data reader module, what it will do is, when I run the program, it'll take a bit of time. And let me make sure I have actually run it. Okay, yeah, it is taking a bit of time, but it's essentially what it's doing. It's produced this chart. Okay, it's produced this chart, and this chart is from real data from Yahoo, or from 2017 to 2022 of taken at monthly intervals of Tesla's share prices. So it's gone to Yahoo, that's the data source. Yahoo essentially, it's gone from the start date to the end date, okay, 2017, January 2017 to the end of December, if you like, 21, and it's plotted all the at monthly intervals, all the values of Tesla stock markets. So again, this is part of the Pandas package, which I think is quite amazing, that you can actually do things like this fairly readily in a program environment. So now we come to sort of more data mining things: regression, analysis tools, correlation, classification, and cluster analysis, which are again very, very interesting things to be able to do in analyzing data fairly regularly. Now, regression, you've got essentially linear regression, which is essentially a straight line. You've got a multilinear regression, which is you're trying to model things with this type of equation, and then you've got what's called polynomial regression type models, which are this type of model. Now, in regression, you have what's called the coefficient of determination, and if r squared equals 1, it means you have a perfect fit to the model. So if these are your data points, like this, the green points here, essentially this model here, the black line, is your estimated regression line using linear regression model. Okay, so we can actually do this fairly readily in Excel. So if I just, you bear with me, let me get my regression model, S regression 01, S regression 01. So this is, again, how we create a regression model. This, if you like, is our data creation in arrays. This particular, we're just constructing a color map to make things easier. And essentially what I'm doing is producing a scatter plot of my X and Y data, and I'm showing it here. Now we get into the actual modeling bit of the area. So I'm performing my linear regression, or creating my linear regression model using this particular function, or class, I should say, doing my fitting, then taking my fitted model and creating, if you like, updating my model and doing a fit again, getting my intercept and my R coefficient, and then doing my sort of prediction model. So if I run this particular model, what happens is this is the basic data, scattered line, and what it's produced finally after doing the regression. It's done the scattering, color coded the data, provided a color bar, and then provided this, if you like, my model of the best fit. And if you look, you can obviously print some of these values out in your terminal window and calculate your R value and have an idea how well your model fits the real data, like that. Similarly, this is actual model, doing a bit of modeling. And then this, again, please read the documentation on how to use these functions properly. It's readily available. And now we go on to correlation. Now there are three main types of correlation: Pearson's, Spearman's, and Kendall's. And again, if we very easily done in MATLAB, so it's not MATLAB, sorry, in Python. Let me just get the file, correlation. So what I'm doing here now is I've got some data. I'm using putting it into a data frame, essentially. And here, if what I've got, I said, it's I've got my x values and my y values, and putting these into a data frame, then manipulating the data frame to get my correlation for a Pearson, Kendall, and a Spearman fit. And if you see what happens now is that we have this is my XY data, if you like, and then this is my Pearson coefficients, my Kendall tau, my Pearson, yeah, Kendall tau, and finally the Spearman coefficients. And there are some differences, as you can see, in the values, depending on which of the correlation coefficients you use. Again, this is this particular example. And then we go on to classification. And again, this is a classic model that people use, and there's the data is based on some research, I think, done in the 1940s in the UK on the flower, the iris. So again, what you're doing importing your data from a CSV file, putting into a data frame. Then you're actually creating plots from that data using, again, various arguments to the pair plot function of SNS, which is your Seaborn, which is another package, which is a visualization package. And then you do some testing, again, doing some sort of training of to get your analysis done, creating a model and doing a model fit, and then some prediction, and then finally sort of producing your results. So if we look at this particular model that we have here, iris classification 0, 1. So what happens here is classification 0, 1. That's the essentially code for the iris plots, and what happens is you can run your code, and it obviously gives you some tabular information, but you can also produce this type of plot using SNS to visualize your classifications and your legend, to sort of give you an idea of what is happening in your data. That's again classification. You can also do cluster analysis as well, and there are various algorithms that you can use, which I won't go into depth here, but one of them is so-called affinity propagation. And if we look at what happens here in the affinity propagation, note, I'm not sure, I don't think I actually have an example of that readily available, the code, but it would essentially, let me just see, do I have clustering 0, 1? It could be clustering 0, 1. data set, features. Yeah, let me just try that out. Yes, so essentially what you have, you've generated some data using 500 samples, and essentially your data is in sort of two clusters, and you've got some outliers here, and some potentially missing data here and here. So you can do, and this is obviously on a scatter chart, fairly readily in Python to show you clusters of data that and how they lie, if you like. And finally, we've got a few minutes we've got left for visualization. Now, these are, again, packages that are very good to install in your Python. Again, if you're dealing with WebGL, JSON, or JavaScript, these are good libraries again to implement. But obviously, to use them, you've got to read the literature about how to use them effectively. Now, I'm just going to quickly show you some of the things that you can do with Matplotlib and Seaborn. Now, you can create charts like this fairly readily with code, simple code like this. It doesn't take much, and this is essentially using a Matplotlib, which is derived from MATLAB plotting library. So there is a commonality between that, and as you can see, link space and sin t. So I've generated my data, plotted it out fairly readily. You can create 3D plots, again with relatively simple code like this. Here, you're importing the appropriate libraries, generating your data here, creating. Is it possible to create an editable figure window? Well, you will see. The answer is offhand. I don't know the answer to that. I suspect the answer is yes. It depends. I think on what exactly you mean editable, but you'll see a bit later. So here I'm creating a mesh grid, which is similar to MATLAB. And then this is the function, plotting it out, and then using a plot underscore surface to create the surface. And obviously here I'm using a color map argument to give you this different range of colors and the the vertical color map depending on the value at the side. So again, fairly easy to do color maps like this. Scatter plots, again, you can get scatter plots and you can put them on your web browser. So you can actually create data that goes into your I suspect you can do that. I mean, if you mean by edit, you can change through code the looks on your, if you like, or the annotation, for example, on your figure. Yeah, you can do that in Python. You can also have highlight specific points and add markers and if you like, arrowheads with lines to specific points on your plot. Yeah, you can definitely do that in Python. That's what you mean by editing. Either in your figure objects, like here, that you've created essentially a figure object. You can manipulate your figure or your graphics object with code. You can also generate on a browser things like this. So essentially, as you can see, it's on a browser. It's got a horizontal scroll bar, and as the user changes the scroll bar from left to right, you can change the frequency of the sine wave fairly easily on your scroll bar, sorry. And you can also have animation. Now these are some sort of good links to animation in MATLAB. Now one of the things that you can actually animate, I'm just trying to find the file, if I can find it fairly readily. Let me just check on my PowerPoint. Yes, simple 3D anim. Okay. So I need to find my file, simple 3D animation. If you just bear with me in the last moments. Well, let's see if I can actually go to the website. But I've lost the plot now because I can't actually. It's not in the folder that it should be in. So I'm not going to waste time trying to find the file. But essentially, using Matplotlib, you can create 3D animated files fairly readily. And these are again some websites to show you some of the things that you can animate MATLAB. And finally, what you can do is create your own GUI, which is graphical user interface. And so here, this is an example of a simple calculator that you can create. And that should be readily available in my folder. My GUI folder, where is my GUI folder? GUI. There's my GUI file. Okay, so this essentially is a series of functions that you've created for various operations in your code. You're using tkinter, which is the sort of Python standard GUI interface package. I've created some functions here to do the addition, to do the subtraction, multiplication, and division, to clear the actual display area, and to actually do the calculation part of the file. Again, these are using if, elif statements, and depending on what happens, you can create it. Here, I'm actually using the button controls, different button controls, or widgets, as they're called in tkinter. And you can have labels, you can have all sorts of widgets. So if I actually run, if I run this program, what happens is it produces a little window here, and I can type in, say, 3 plus 4 equals 3 plus 4 equals 7, and then I can clear it. And you can build very sophisticated applications with that are menu driven, so the user doesn't actually get into the code. They just have this window as an interface to the code behind your program. And that, I think, is the end of the presentation. A bit better on time, that we've covered all the material. And again, please do fill in the feedback form, the Google form that's shown here, which I put in the chat earlier on. And that, I think I'm not too much over time, 5 minutes over time. And that really is the end of the presentation on a bit more of the advanced features of Python in engineering and data analysis. And really, it's only the tip of the iceberg. As it is with packages like MATLAB and Simulink, you're only in 1.5 hours or even 3 hours, you're only looking at scraping the tip of the iceberg, because they are huge environments that you can explore. Okay, any questions? Right, yes, Catherine, what is your question?
Okay, can you hear me?
Yes, I can.
Okay, thank you for the presentation. It was a long day, actually.
It was a long day.
Yeah, more for you, actually. Yeah. So I have a question, not related to this one, but I have one code. Okay, and so I want to convert the format of a data from using NP arrays. But I run into problem while converting the dates, you know. So I don't know if you can, if you have.
Right. My best dates in Python itself are pretty basic. There are some nice packages that you can actually install, which make date manipulation far easier than the standard that you get with the Python installation. I can't think of the names offhand, but if you drop me an email, I can. I'll give you the names of a few of them that will make manipulating dates in, if you like, a data frame, for example, or an array a bit easier.
Yep, sure. And will you be available sometime that on a meeting and that we can look into the code and maybe fix it?
Now, basically, let me explain a bit more on this. Essentially, I work for the SSU Centre. On WCO, we have a booking system and I try to run workshops on Python and on MATLAB. So if you book a session on WCO, then we can discuss code on a one-to-one, or I can actually create a specific appointment for you on WCO, and it'll just be me and you discussing your particular problem. That can actually be done, but please
sounds good. Yeah.
Good. Khalid Galal. It was done using plot.ly, not matplotlib, to answer that question, which is again is one of the nice packages that is available. And as I said, in fact, it's now over 4,500 different packages are available for you to look at and install. Like on my installation on my at home, I have, for example, a LaTeX package installed. So if I want to produce very nice looking, if you like, vector graphics on a paper using various equations, etc., rather than raster graphics, which you get with bitmaps and what have you, you can actually do that using this package. I said there are actually tons of packages that are available, and it's well worth looking into what packages are readily available. In fact, somewhere I have an Excel file that has about 4,000 packages that are listed, and it takes ages to actually go through the Excel file. But so now there's more, I think, than 4,500 packages available in all sorts of areas. And the nice thing is that being open source, if you become proficient in Python, you can actually write your own package and have people use it all over the world. So any other questions? Okay. I assume that is a no. And in that case, I will say arrivederci. And have a great weekend and keep safe. Thank you very much for your time. And I hope to bump into you again, either online or actually physically. All right. Thank you very much and goodbye to everybody.